Hello, everyone. Welcome back to this series on statistical analysis in Python, and I hope you're enjoying this series. And for those who just joined us, new, I definitely recommend watching the first set of videos I have done as part of the statistical analysis in Python, as that may help you understand these topics much better. So if you haven't already done so, this may be a good time to hit the subscribe button, find it down there, and while you're there, try to find the little thanks button if you're feeling extra generous. Okay, let's jump into the topic. This one, of course, is about dimensionality reduction, and we'll explore what it means, and we'll focus on principal component analysis for this one. And in the next one, we'll look at a couple other ways of reducing the dimensions. Now, first, let me go to the next slide if I can. First thing first, what is the challenge with high dimensions? What do we mean by high dimensions? Well, oftentimes we work with data that has a lot of features, whether it is sales data or it can be like scientific data. For example, if you have an image of a tumor and you're trying to see if it's cancerous or benign, then you may perform various measurements that includes texture and a whole bunch of measurements, right? So you may have like 20, 30 different measurements in this example. In real life, you may have certain scenarios where you have hundreds of features or attributes. You cannot just plot all of those and then visualize, right? We only plot 3 at a time. So that's the high dimensional challenge. Visualization is a bit difficult, and we are humans. We want to look at things and we want to make decisions based on how things look at. And also computational complexity, as the number of features or number of dimensions increases, of course, it increases the computational complexity. Same with storage, although storage is a bit cheaper, I should say. If you want to put this in long-term storage, you may want to cut it down to the top 2, 3, 4 principal components and minimize the data, and you can reconstruct it back. We'll get to that later on. And also overfitting risk. If you have, let's say, 100 different attributes or features, like columns in your data, but then you only have 50 data points, that doesn't make sense. It happens. Those type of things actually happen depending on what type of data you're gathering. But if you have more features than samples, that definitely leads to poor generalization. So you may want to collapse those 100 features into like top 2, right, for machine learning purposes. So these are some of the reasons. And again, when do we need dimensionality reduction is an answer to the challenges. Basically, if you have more than 10, 20 features, you want to cut it down. And especially, I want to focus on these correlated features because there's a lot of redundant information across variables. For example, if you have, going back to the tumor example, if you have, let's say, area and perimeter and all of these, related, like radius, they're all related. You just need one of those. Others can be calculated from one measurement, right? So then it doesn't make any sense to have all those features. Then you can collapse those. So there are a few other reasons why you need to actually reduce the dimensions. Now, coming to principal component analysis, there are various ways. There are at least 2 or 3, let's say 3 top methods to reduce the dimensions. And principal component analysis is the one that's probably the oldest and also the most commonly used technique. It's basically a dimensionality reduction technique, and it, as the name suggests, it transforms your high dimensional data if you have 30, 40, 50 features and only condenses it down to, let's say, 2 or 3 features, let's say. Of course, the key point here is whenever you do that, you're going to lose some information from your data. And that's what this second line is, preserving as much variance as possible. Variance is basically information content. Variance is along the direction how is the data distributed. So that's basically the variance. If there isn't much variance, you don't have a lot of information, right? So we'll get to that. Hopefully it makes sense once we look through a couple more slides and then jump into the code. So the key components here is the principal components. We're basically components think of this as new features or new attributes that are calculated, that are a combination of your original feature, and it's a linear combination. That's very important because later on we'll see nonlinear methods to reduce the dimensions. But since this is linear combination of original features, we should be able to, it's a reversible transformation. We can reconstruct the original data using this linear combination of variables, right? Obviously, if you don't use that many variables, then your reconstructed data is not as good in quality. Keep that in mind for now. We'll get to that in a minute. And variance maximization, we already established that variance is information content, so you have to maximize the information. So each principal component captures the maximum remaining variance. What does that mean? If you just start out, the first principal component covers the maximum, meaning it may have 40% of information captured. The next one probably captures 30%, and the next one 10%, and the next one 5%, and so on, right? So that's what the variance maximization basically means. And also orthogonality means these are perpendicular to each other. In other words, each principal component is uncorrelated, right? So obviously this speaks to the previous fact where we talked about correlation, where radius and perimeter and area, they're all highly correlated. They're not orthogonal, right? When you take those features. So principal components, they're orthogonal. Of course, you're trying to reduce the dimensions right there. So if you're still confused about what's happening, here is a quick example based on what we're looking at. We're going to look at a data of 30 measurements from tumors from cancer patients. And there are various parameters, but if you look at the tumor size is a function, it can help you distinguish between malignant and benign. Otherwise, you don't have maximum variance. What do we mean by maximum variance? Maximum information, by which we mean, if you look at tumor size, we should be able to tell the difference between the malignant and benign cases if you look at tumor size. So that's high variance. Maybe it's a function of patient age, but not a strong function of patient age, so it probably varies only a little, right? The patient age as a function of, the benign or malignant as a function of patient age in this case. So this is a low variance direction. This is a high variance direction, tumor size. So I hope that makes, but in this case, I'm just showing you one example, but it's a linear combination. It's not just tumors. When we say tumor size, it's like the area, and it may be something else and something else. It's a combination of that gives you your principal component right here. Now, the PCA's job, principal component analysis job, is to find these directions of maximum variance because they have the most information. That's it. In our example, we will later on see that our principal component number 1, usually referred to as PC1, it contains 44.3% variance, meaning just by using this one component, you can actually regain 44.13% of information in the entire data set with 30 different features. On top of that, if you add the principal component number 2, it gives you extra 19% information. Basically, by combining these two, you can reconstruct 63.3% of total variance. In most cases, this is not bad, actually. You can just take this, all 30 features, collapse it down to these two, PC1 and PC2, plot them on 2D. You see a scatter plot, apply k-means clustering algorithm to separate them into 2 clusters. There you go. You have your classification. We'll do that actually later on. Okay, and the math background, a quick, like how do we approach this? First, step 1, data centering, because the data may not be centered because we're treating a whole bunch of features. In fact, before data centering, we will have to do some sort of a scaling of data because the age goes from 0 to 100. But the tumor radius is 0 to 1,000 microns, for example. So it's a different measure altogether. The area is obviously 2 orders of magnitude more than your radius. So things come in different sizes. So you kind of do data standardization. By definition, when you standardize data, it automatically centers the data. And once the data is centered, you can actually calculate covariance matrix, which is, okay, I have feature 1 and feature 2. What is the covariance? We talked about this correlation in the last few videos, so that's why I think you should watch those first. But anyway, coming back to this step, so between each pairs, you look at covariance and you create a covariance matrix. And diagonal elements obviously are variances of individual features, and off diagonal are covariance between feature pairs, feature 1 versus feature 2, area versus texture in our example, for example. Yeah. Once you have this, then you calculate the eigen values and eigenvectors. So this is called eigendecomposition. So you calculate the eigenvalues, which is basically the amount of variance, and eigenvectors is the direction of these principal components. Once you do that, then the next step is, let me go ahead and click again. I mean, these are the steps, but if you want to look at a summarized table, step 1, like I mentioned earlier, standardize. Once you standardize, by definition, the features are centered, the values are centered, and then you calculate the covariance and perform the eigendecomposition. Then you get your eigenvalues. Then you just sort them from descending order. So the first 2, 3, 4 are the ones that we want to pick, and then you can transform, or you need to transform the data, your input, 30 features or how many, into your principal components, and you can also reverse transform back to original if you need it. Now the question is how to choose how many number of components. Okay, you have principal component number 1, 2, 3, 4, 5, 6, and these are the eigenvalues of each. And eigenvalue tells you the importance in a way of each of these. Eigenvalue of 1 is called the Kaiser criterion. This is often used as a criteria to pick the number of components. On the plot, you can see if you pick eigenvalue of 1, which is the red line, as your criteria, then you need 6 components, the first 6 components, to retain enough information. In a way, if retained information is your goal, then a better way of looking at it is you can say, okay, I'm comfortable with 80% variance, retaining 80% information, and 20% can be gone. And by the way, this completely depends on your application. If your application is using this for machine learning classification, then 80% is more than enough. In fact, even 60% is more than enough, as we'll see later on. But if your goal is 80%, that's happening right around here, which means you need 4 components, the first 4 components. I hope this makes sense. And now it's time to jump to the code and start making more sense of principal component analysis. So let's go ahead and jump in. So I'm working on Google Colab, so you guys can easily recreate what you see here on the screen, and the link to the code is down under description. And I've added quite a bit of notes, probably similar to what you just saw in PowerPoint with a bit more context, I would say. And I talked about dimensionality. And in our case, the data is we have 569 samples. That's way more than 30 features. Great. So at least we don't have more features than data points. And we have 10 characteristics like area, radius, perimeter, texture. So we have 10 such characteristics and 3 measurements for each characteristic. For example, there is mean area. There is standard error, for your area, and the worst. So they're like these 3. I have to remind myself what the worst means. But anyway, there are 3 variations of area: mean area, SE, and worst. And SE, I assume that's the standard error. Yeah, we can look at documentation if you're curious about what exactly these 3 are. And of course, the 2 targets are, is it malignant or benign? Is this a specific data point coming from a malignant tumor or benign? So that's our data set. And what we will discover, I kind of gave you, ahead of time, but we'll see that soon. Okay, the libraries are pretty straightforward. I'm going to use pretty much the standard ones. Scikit-learn to learn the breast cancer dataset. You can alternatively download this as a CSV file and you can load your own. And I'm using standard scaler again because we need to scale our data to bring everything, all the values between 0 to 1, and then center it. So that's what standard scaler does. And of course, principal component analysis. It comes, there are various libraries that offer PCA. I'm going to pick the one from scikit-learn.decomposition. Although we will do certain stuff manually, but yeah, PCA itself coming from scikit-learn. And moving forward, let's go ahead and load the data set. Since it's coming from the library itself, all you do is load breast cancer. and you kind of separate it into your X and Y values. X is all the features. Y is basically either it's benign or malignant. And we are capturing that into a pandas data frame. And the first part just summarizes what is loaded, and as expected, 30 features and 569 data points. Okay, the next step is analyze the high dimensional characteristics. We want to see what the correlation is and how different the scales are. So that's between various features. So that's basically what we are printing here. And again, we have 569 features and sample to feature ratio. How many samples do we have versus how many features? We know that that's pretty good already. And scale ratio, maximum versus minimum, it's 105. I mean, that's a pretty high value. We know that we need to standardize. So I'm just checking this. Sanity check is standardization. Sometimes datasets come with pre-standardized, or naturally they're standardized for whatever reason, but it's worth checking it. And also correlation, we are looking at, you will see .corr at some point. Yeah, right there, NP dot correlation coefficient. So we are looking at the correlations, and the correlation is, all I'm saying is, hey, go ahead and look at correlation. By the way, watch our previous videos. This is basically a Pearson correlation coefficient of 0.8. We know that very high. So I'm printing all the correlation, or number of correlations, number of features with correlation higher than 0.8, 44. That's a lot. Because we have 30 features, we have about 400, 450 combinations of features, and of those 44, 10% of them high correlation. I bet they are area, perimeter, and those ones, but at least this gives you an idea of which ones are, how many are you dealing with. Now let's go ahead and visualize it. All I'm trying to do is visualize the correlation heat map and our feature distributions. So this is just a plot and a scatter plot, right? So right there, the bar plot, you can see the area values are around 600 to ish, and then with a very high deviation right there. And you can also see perimeter is right here, texture values. These are very small. So of course, standardization is needed. And the correlation matrix, you can see there is a lot of red hotspots that tells us that there is high correlation. And again, if you look at correlation, you can see perimeter is highly correlated with radius. Area is highly correlated with perimeter. So these are all something, expected. Not much negative correlation here, but mostly positive correlation. Okay, and feature distribution, of course, this tells us that if you look at the mean radius, one feature itself, you can kind of separate the malignant and benign right here. So the red is malignant and the bluish is benign. Also, when you plot, scatter plot, mean radius and mean texture, now you're adding the second feature. Now you start to separate these two a little bit, but you still see a lot of blue points right there. So let's hope by collapsing all of these into two principal components, instead of looking at two separate features, we will get better separation here and better accuracy when you perform k-means or support vector machines or some sort of a classification. Okay, so next one is, okay, now you're probably naturally curious about, okay, which ones are highly correlated? So I'm just printing. That's basically this part. So the top 10 correlations are radius and perimeter. I have no clue why it's printing twice. I have to go back. I think one is radius mean versus perimeter mean. The other one is radius SE versus perimeter SE. I should have printed the whole thing, but these are highly correlated as you can see. I'm glad that I don't see texture is correlating with radius or something. It's not at least highly correlated, about 0.8 or something. Okay, with that information, now we know that we need standardization. So let's go ahead and standardize the data and then implement our PCA. So standardization is, we are going to import it directly from a library, but it's nothing but your individual data point minus mean divided by standard deviation. That's basically what standardization is. So by definition, that brings your values to between 0 to 1. Okay, and equal importance for all features is needed for our principal component analysis, and standardization helps us do that. And once that's done, data is centered. You look at the mean, the covariance matrix, and then from the covariance matrix, you take your elements to calculate the eigenvectors. and eigenvalues, and from there you basically have your transformation equation right there. Okay, because once you have the direction of principal components, you just take your centered data, multiply by that to get your data projected onto this principal component space. So that's basically what's going on here. So we are going to standardize it using, here I'm actually showing you before standardization and after standardization, printing out a few values. But for standardization, we are using standard scaler. Okay. Again, it removes the mean and scales to unit variance. That's the whole point of standardization. So let's go ahead and run and print it. So before standardization, here are the feature values. And after standardization, of course, they have to be centered and with a standard deviation of 1. Okay. So now all of these can be treated equally from a principal component analysis point of view. Okay, we are ready for performing principal component analysis using the standard data, not the original data, right? So we have standardized it. So how do we do that? Okay, we take your scaled values, and of course you get your number of samples and number of features right there. And the step number 1 is to center the features, but they're already centered. So we're not performing any centering as a separate step. By standardizing, they are centered. And calculating the covariance matrix, again, there are various libraries. NumPy is one I use if I can most of the time. So numpy.covariance gives you the covariance matrix, and T stands for transposing those values, and you get the covariance right here. And then Eigendecomposition. I'm doing this manually here. You can just directly apply .pca and then you get all these, but you can see the guts by doing this manually. So from within NumPy, within linear algebra, you have eigenvectors and eigen function method that gives you eigenvalues and eigenvectors. Let's actually run this first. And then we are sorting them in descending order. And we are actually looking at how much variance is explained by these. It's basically you look at the eigenvalue divided by the sum of all eigenvalues. The percentage tells you how much actually the variance is being explained. And cumulative variance is just for plotting. So you can see by adding n number of components, how much cumulative information you are actually gaining. That's for plotting purposes. And now I'm, again, for plotting purposes, setting a threshold of 80%, 90%, and 95% just to see what gives us, what combination or how many principal components is going to give us respective variance or information. We have already executed that. So you can see 569 samples, 30 features, of course, data already centered, and covariance matrix shape is 30 by 30. We obviously know that because you have 30 features and you look at 30 combinations. So you have 900 of them, but then you only look at the half of this. The other half is a repetition of the bottom half. So in a way, you have 450 combinations. Of those, we found like 44 of them are highly correlated, right? Which is 10% of the combinations. Eigenvalues right there. Eigenvalues sum 30.05. I mean, they should add up to about approximately how many features you have. We have 30 features, so not bad. And variance explained. So the first principal component has an eigenvalue of 13.3. And if you look at the ratio, you get 0.443, which means it explains 44.3% of information contained in our original data set. Now, if you include the second principal component, you get 63%. Third, you get 72%. So if you need 80%, you need either 4 or 5 principal components, then you get 80%, right? So once you cross like 10 principal components, the incremental gain of information is not much. So typically 6 or 7 is okay. Okay, so 80% various, 5 components, we already looked at that. Now let's go ahead and analyze these components, meaning let's go ahead and do that. If you get high value, that means that feature is very important for a specific principal component, because the principal component is nothing but a combination, a linear combination of individual features. And if for a given feature, the multiplication factor is very high, like let's say 0.3, that means that feature is contributing 30% to that specific principal component. So it's probably very important. Otherwise, so we're just decomposing this to understand better in terms of how our principal components are, assembled, created. So the principal component number one, the first one that explains 13.3% of information, 13.3 eigenvalue, which is about 44.3% of information. Here is the combination. So mean concave points, 26.26. Mean concavity, 0.258. And I think it likes the concave measurements and compactness, perimeter, and concavity. This is all feature principal component one. And component two includes fractional dimension, whatever the mean fractional dimension. I can't read the rest of it. Mean radius is part of it, compactness, error, and mean area. So you get the point. So this is a way of seeing what components are contributing by how much to each of these. That's basically it. But let's go back to our PCA, principal component analysis, and see further analysis. Like scree plot actually tells you visually, you can actually look at it and pick like how many components. Cumulative variance, you saw that on our PowerPoint cover slide. Why am I talking? Run this and show you the plots. You don't have to imagine what these plots are. We are literally plotting them. Okay, scree plot is principal component versus what their eigenvalue is. And if you're following Kaiser criteria of minimum eigenvalue equals to 1, or eigenvalue equals to 1 is the threshold, then you get 6 components as the number of components that you should be picking for your downstream analysis. Okay, or basically number of components, you're looking at cumulative variance. Remember, we kind of captured this, and you can see that, okay, if you have 6 components, you get about 89-ish% of information with 6 components. And here is another way of looking, like principal component 1 and 2. If you take the first 2, then probably, look, there is almost like a straight line right there that we can draw to separate benign and malignant. That tells me maybe this is a good, 2 components is good enough for my k-means clustering, maybe. And here, this plot, it shows you the component loadings. Loadings is nothing but the contribution of each feature, for example, and I'm only taking a handful of these features. So if you look at mean radius, for principal component number 1, the mean radius, blue means negative loading. So as the mean radius value goes up, the principal component 1 value goes down for that specific feature. So that's what the loadings map is. Again, this can be useful if you look at it. One thing that tells me is for PC1, it's a negative relationship with all of these, right? PC2, you have some positive, some negative, and PC4 looks like strong positive here, strong positive here in terms of contribution. Okay, so I think that's good. And now component selection, 3D visualization, quality assessment. So how many components? We already saw like top 6 components, but I'll just show you a couple other plots and visualization, and also quality assessment. This is very important. So in this section. So let's start with component selection. We talked about this quite often, so nothing should surprise you. One method that people see is elbow. Did I include that? Yeah, the scree plot elbow. When you plot that principal component versus eigenvalue, wherever the elbow is, that's probably a good place. So let's go ahead and look at this. Elbow method. Oh, this is just a printout. What I mean by that is, if we go back to this plot, if you look at this plot, the justification is wherever the elbow starts, the gain on information is not much. So you may as well pick the elbow. So some people may say, oh, the elbow is at 3, or maybe it is at 4. Again, it's up to you to figure out where that elbow is. So that's one way. In fact, and the best way would be how much variance you want to retain. That's one way of actually picking how many. Kaiser criteria is also good. You'll end up with 6. Scree plot elbow, it points suggest only 2 components because the third component, it's already flattening it out. So maybe if you take 2 components, you're good. And yeah, I think that's the summary of that block of code. And now let's just look at 3D visualization, because you need 3D for 3 principal components, right? So with 3D, we may get better separation actually between these two, between malignant and benign, right? So, but that's a nice visualization that shows us. I can't see what's going on at the interface. This is a static plot, but if you can zoom in, use Plotly for plotting, then you can probably zoom in to see if we can draw a nice straight line between the data points, or plane between the data points for our k-means type of separation. Okay, now what's important now? So we know that, okay, we get a let's say 60%, 63% information if you pick the top 2 principal components. This is basically another way of actually confirming that, I should say, assessing reconstruction quality. Okay, you take 2 principal components. What happens if you reconstruct all the 30 features? When I say reconstruction, you go from the principal component space to the real space where you have all features, right? So all we are doing is, reducing the dimensions from 30 to 2 with 2 principal components. And now we want to go from 2 back to 30 to see how the reconstruction looks like. That's all this is. Yeah, reverse transformation. So as you can see, reverse transformation right there, reconstructed. So reverse transformation, and once you get the reverse transformation, how does it look like? Of course, as you can expect, if you only have 2 components, the reconstruction error is 36%, right? Because we know that information retained is 63 point some percent. Okay, so the remaining is the reconstruction error or the information lost, 63.2 right there. So information loss is 36%. With 5 components, 15% loss, and I think with 10, of course, you can see 4.8% loss and so on. Now, visually, let's go ahead and look at that in a visual way. What do we mean by visual way? I'm trying to reconstruct every feature for 2, let's say, components and 5 components and so on, and then just plot it and see how much variation there is. So first thing first, quality metrics visualization. As you can see, as the number of components increases, the reconstruction error decreases, and of course the information gain increases, or variance retained increases, same difference. This is something we already saw. These are eigenvalues versus principal component. And this is nothing but the scree plot in a different scale with a log scale right there. But you can just compare the reconstruction samples, yeah, down to the individual data point, down to the individual feature. So once you reconstruct, for example, with 2 components, for each of these, you can see the original is the blue and the reconstructed is the red. Of course, some overlap, some difference right there. And if you have 10 components, now you start to see better match, better information regain for all the features. Here, for some features, you don't have a good match. Now, that's sample number 0, first data point. Look at 1/50th data point, from our actual data, 1/50th data point. Again, if you have 2 components, in this data point, error is 88%. In the data point number 150, error is 50%. So of course it's different between different data points. We're just seeing how well we can reconstruct these data points. These features for different data points, and this one is horrible. This one, with 10 components, it looks good. With 5, it starts to look good. That's why I think with Kaiser criteria of lambda equals to 1 or eigenvalue equals to 1, with 6 components, we should be pretty good. Okay, all that is great. Now let's just look at, okay, we do PCA, what good is that? How can we perform machine learning? For example, if you want to classify these into 2 classes. So that's basically the exercise here. And the steps we're going to follow is we take our data, we split the data into training and testing. Always do this first. In most of my earlier videos, I didn't bother about doing this because I thought, oh, these are just tutorials, so let me just show you the steps. But I realized it's very important. You're, after all, learning from these videos, I hope. So good practice. Split the data first before doing any processing, and then scale them independently. Training and testing data sets, scale them. And then transform the test data using the same scaler that you have done using the training, right? So exactly the same way. And then fit the principal component analysis on training data only, and then transform the data using the same principal component analysis. The test data using the same principal component analysis. Okay, and then you that order obviously matters. And then once we have that data, we classify them using k-means and support vector machines just to see how they both differ. Because k-means it draws a straight line, and support vector machine draws a curved line to find a better boundary between these two classes. So we expect support vector machines to do better. And we'll quantify that using accuracy metric. Okay, and then we'll do 2D plots. So let's go ahead and run this, and this is doing exactly the same steps. Okay, so we have our data. We're starting with the data. We loaded that, and we prepare the data here. So how do we prepare that? Again, we standardize. We apply principal component analysis. Only we fit it on the training data, and of course also scale it. But then we transform the test data using the same PCA that we just created earlier, right here. Okay. Once that's done, you'll see that, okay, we have PC1 45.2%. Earlier we saw 44%. Right now you see slightly different numbers because now we did split training and test data. So we're applying on different data here. Okay. And now let's go ahead and visualize the principal component analysis data before applying our machine learning algorithm. And you can see that training data in PCA space, between PC1 and PC2, this is the training data, that's the test data. I like to see similar patterns between these two. That tells me that the data is nicely split. Otherwise, if you see different patterns, you're like, okay, what's going on with your data? It's got to be random. Both need to have similar shape, and in our case they do have similar shape. That's great. Okay, now it's ready for our machine learning, and let's do unsupervised, which is k-means clustering. And again, I'm fitting and predicting on the training, and then only predicting on the test using the already fit k-means on our training data. This is how we typically do. I don't know why I'm explaining. Maybe some of you are new. And once that's done, let's go ahead and look at the accuracy, because once we have the test data, we can calculate the accuracy, right? So k-means accuracy on our test data is 92.4% accuracy. That's great. We took 30 features, collapsed it into two, principal component 1 and 2, and we performed k-means unsupervised and achieved 92.4% accuracy. That's amazing. I hope you appreciate that. Let's perform exactly the same type of classification, except instead of k-means, let's go ahead and do that on our using support vector machines. Again, I did a video a long time ago on this topic, so go ahead and search for that on my channel. Let's go ahead and run it. Very straightforward. You call support vector machines from scikit-learn. Go ahead and apply .predict or .train, like right there. There are various kernels you can use. I'll just use the default, I think. And once you define the support vector machine object, then you can fit it on your training data. That's what we're doing. And once you train it, I'm using that and predicting on my test data. And once you predict, you have your original data, test data, y values, like whether it is malignant or benign. And then you have the predicted values. I'm just checking accuracy. That's it, and printing it down here. So our accuracy here is almost 96%. That's amazing. Of course, it's better than k-means because here it's a curved. It's not a straight line that's actually separating these two. So you can compare this visually if you don't know what I'm talking about. What do you mean by curved and straight line? I just plot the decision boundaries between the malignant and benign using k-means and using support vector machines. So the decision boundary is a straight line, as you can see, and some of the red dots, the malignant ones, are being classified as benign when you do principal component analysis, which is where we get that error from. And when you apply support vector machine, you still have a few data points of malignant that are misclassified as benign, but still the number of them is very low. Well, we can always plot confusion matrix to see how many misclassified ones. So let's go ahead and scroll down and end this video. So with k-means, you have 11 such data points. With support vector machines, you have only 5 that are benign and labeled as that are malignant but are labeled as benign, because this is predicted on this axis. Okay, so I think this is good. And final summary is basically, let's put all of them together, and you can see original 30 features are principal components. In this exercise, we got it down to 2, and which means 15 times dimensionality reduction, and our variance retained is about 65% of information is retained. And with that information, we successfully classified 92.4% accuracy using k-means and 96% accuracy using support vector machines. Okay, that's turned out to be a rather long video. I appreciate you sticking around. And in the next one, let's go ahead and look at a couple other ways of dimensionality reduction, relatively modern compared to PCA, but I hope you appreciate that video. So come back. Until then, please hit the subscribe button. I'll see you next time.